And before we move on, let us introduce. Let me introduce a very famous person called Karl Pearson. And Karl Pearson is an English mathematician. He was a pioneer in the development of mathematical statistics, and he founded the world's first university statistics department at University College London in 1911, slightly more than a century ago. And when the 23-year-old Albert Einstein started a study group, the Olympia Academy, with his two younger friends, Maurice Solowine and Conrad Hilbert, he suggested that the first book to be read was Pearson's The Grammar of Science. And this book covered several themes that were later to become part of the theories of Einstein and other scientists. And Pearson chi-square test is one of the most famous tests developed by Pearson. And this statistic is used by statisticians to describe how well a theoretical hypothesis fits a set of observations. Specification or stochastic modeling of data is an important step in statistical analysis of data. And Karl Pearson, he was the first to recognize this problem and introduce criterion. He published a paper in 1900 to examine whether the observed data support a given hypothesis or specification. And the test was called the chi-squared goodness of fit test, which motivated research in testing of hypotheses and estimation of unknown parameters, and led to the development of statistics as a separate discipline. And in an article trial by Number, Ian Hacking, Science publication in November 1984, says that the goodness of fit chi-square test ushered in a new kind of decision-making and gives it a place among the top 20 discoveries since 1900. For almost 1 century, among all disciplines, he has a place on the top 20 discoveries since 1900, considering all branches of science and technology, while C.R. Rao and other famous statisticians commented that this test was the dawn of statistical inference. So basically, the Pearson chi-square test deals with the count data, or what we call the analysis of enumerative data. For the first thing we would like to look at is the so-called one-way classification problem. For example, the classification of people into K income brackets. For example, the lower socioeconomic status, the middle income group, the higher income group, and so on, okay, would give counts to each of the K classes. The classification of people according to their responses to the question, do you support CY to be the chief executive of Hong Kong Special Administrative Region, with K equals to 3 options, namely yes, no, or no comments. Okay, this is also a classification problem. Classified people by gender, male or female, or classification of people by age, the 3 age group, old age group, middle age group, and young age group. Okay, these are classifications. Now we simply let Pi be the probability that a randomly selected subject will fall in or belongs to class I, and therefore each subject must belong to one of the K classes, for example. So therefore the sum of the Pi's must be 1. Okay, classification, each subject must belong to exactly one of the K categories. Exactly one, okay? Because a subject must belong to exactly one of the K classes. So the sum of the Pi's must be 1. And the Pearson chi-square test is a very powerful tool in making inferences about the cell probabilities. Okay? And in 1900, Karl Pearson proposed the test statistic, which is given by this formula. This is the formula that would be used throughout the rest of the course. X squared This is the name of the Taylor statistic on the left-hand side. The square doesn't mean anything, and you don't take the square root of this. This is just a symbol, okay? So the Taylor statistic equals to sum over all cells. I will tell you what is the meaning of all cells, and which is the sum of OI minus EI whole square divided by EI. And this is what we call the Pearson chi-square test, where OI is the observed frequency of the ith cell, and EI is the expected frequency of the ith cell under the null hypothesis is true. Under the null hypothesis is true. Okay, and note that the sum over all the observed frequency is just the sample size. And when n is large, the Taylor statistic will possess approximately a chi-square distribution in repeated sampling under the null hypothesis. So what is a let me give you an example before we move on to clarify what is the meaning of OI, EI, and N, and the chi-square distribution, and the null hypothesis, as well as the alternative hypothesis. Let's take a look at example 22. Example 22, it says, according to a geneticist theory, a crossing of red and white snapdragons would produce offsprings that are 25% red, 50% pink, and 25% white in the ratio of 1 to 2 to 1. Okay, so the classification is the classification of the color of the offspring that would either be red, pink, or white. Okay, so an experiment conducted to test the theory produces 32 red, 76 pink, and 36 white offspring in 144 crossings. The question is, do the data provide sufficient evidence to contradict the geneticist theory? Use alpha equals to 0.05. Okay, now here we have K equals to 3 classes. K equals to 3 classes because the classification classified the offspring into one of the 3 colors, either red, pink, or white. Okay, so K equals to 3. Now P1 is under the null hypothesis. That means according to the geneticist theory, the probability of producing a red offspring, P1, is a quarter, 25%, and the probability of producing a pink offspring is 50% according to the geneticist theory. So we have P2 equals to 1/2, and P3, the probability of producing a white offspring is a quarter, 25%. So we have the null hypothesis, which is the geneticist theory, is that P1 equals to a quarter, P2 equals to 1/2, and P3 equals to a quarter, so that the sum of the 3 equals to 1. Okay, and now we have n equals to 144 offsprings, and we observed 32 red, 76 pink, and 36 white. The alternative hypothesis. We specified the null hypothesis, and then what is the alternative hypothesis? The alternative hypothesis would be quite complicated. It could be P1 greater than 1/4, P2 less than 1/2, and P3 less than a quarter, or there are many different combinations. So we simply specify the alternative hypothesis as the null hypothesis is not true, and that's it. Okay, so for Pearson chi-square test, we simply specified the null hypothesis, one-way classification problem. K equals to 3, we specify P1, P2, and P3. Okay, such that the sum of the 3 probabilities is 1. And the alternative hypothesis is that the null hypothesis is not true. Okay, so that is why they call it the goodness of fit test. Okay, if the null hypothesis is appropriate, is good, that means the geneticist theory is good. Okay, the goodness of fit. And sometimes we specify this as in the ratio of 1 to 2 to 1, 1 to 2 to 1. Okay, so then the data actually comes in like that. The observed frequencies, we have 32 red. This is O1, O1, the observed frequency of the first cell. And O2 is 76, the observed frequency of the second cell, 76 pink offspring. And O3 is 36. And N is simply O1 plus O2 plus O3. The total number of observations is 144. Now then, the tail statistic is given by this O1 minus E1 whole square divided by E1. And then for the second cell and the third cell, we sum over all the contribution. Now, what is EI? EI is the expected frequency of the ith cell under the null hypothesis is true. So under the null hypothesis is true, P1 equals to a quarter. So what is E1? E1, out of 144 offsprings, we expect to have a quarter of them being a red color. So that the expected frequency of the first cell would be N times P1 naught, P1 naught, the hypothesized probability associated with the first cell, and P2 naught, the probability associated with the second cell under the null hypothesis. So E2, the expected frequency of the second cell is N times P2 naught. And the expected frequency of the third cell is simply N times P3 naught, which is 144 times 0.25 equals to 36. Notice that the three expected frequencies will also sum up to be 144. Add up to 144. Now then you have everything. It can be easily seen that the expected frequency of the ith cell equals to N, the number of observations multiplied to the Pi naught, the hypothesized proportion associated with the ith cell under the null hypothesis. Therefore, the tail statistic for I equals to 1, we have O1 minus E1 whole square divided by E1. Okay. The second cell, I equals to 2, O2 minus E2 whole square divided by E2. And then the third cell, O3 minus E3 whole square divided by E3. And the tail statistic is 2/3. Okay? Now, the rationale is that if the observed frequency agree closely with the expected frequency, like this one, then X0 should be appropriate. Okay, and the statistic X squared would tend to be small if for all cells the OI agree closely with the EI. Okay, but in any case, in some of the cells, if the OI deviates substantially from the EI, okay, OI deviates substantially from the EI, okay, or the alternative hypothesis is more appropriate, or the null hypothesis is not true. We expect some discrepancy between the observed frequency and the expected frequency under the null hypothesis is true. We expect some discrepancy, and squaring the discrepancy will end up with a large value of the tail statistic if the alternative hypothesis is true. So in other words, a large value of the tail statistic is in favor of the alternative hypothesis. Now, as we mentioned earlier, that when n is large, the tail statistic will possess approximately a chi-square distribution with degrees of freedom k-1 equals to 2 in repeated sampling under the null hypothesis. So what is a chi-square distribution? In earlier page, we mentioned that when n is large, the tail statistic will possess a chi-square distribution only. But now, for the one-way classification problem, we specify that there is a parameter associated with the chi-square distribution, and the name of the parameter is called the degrees of freedom. And for the chi-square test, the degrees of freedom is specified to be k minus 1, where k is the number of levels in the classification. In this example, we have 3 levels, 3 groups, red, white, or pink. Okay, 3 groups. So k equals to 3. And the degrees of freedom associated with this test is k minus 1, number of groups minus 1, which is 2. Okay, so how do we determine whether to accept or to reject a null hypothesis? Bear in mind that if the null hypothesis is appropriate, is true, we expect that the test statistic to be small. But if the test statistic is large, we would consider that alternative hypothesis would be more appropriate. Okay, so what is the properties of the chi-square distribution? Now, a chi-square distribution is characterized by the parameter called the degrees of freedom, okay, df, degrees of freedom. And under the null hypothesis, the test statistic x squared follows approximately a chi-square distribution with degrees of freedom k minus 1, okay, with degrees of freedom k minus 1. Now, this plot gives you the distribution of a chi-square distribution, degrees of freedom 1, 2, 3, 4, 5, and so on. Okay, so I would simply give you the critical values based on the chi-square test for different degrees of freedom. Now, again, the yellow region here corresponds to the rejection region, because a large value of the test statistics will support the alternative hypothesis. So all we have to do is, for a chi-square distribution, we leave alpha probability on the right-hand side, on the extreme side, on the right-hand side. Okay, so for example, degrees of freedom equals to 2 with if we set alpha equals to 0.05, degrees of freedom equals to 2, the critical value would be 5.99, 5.99. So therefore, the rejection region is that if the test statistic, x squared test statistic, is greater than 5.99, then the null hypothesis will be rejected at 0.05 level of significance. So hence, for some pre-specified level of significance alpha, the null hypothesis is rejected if the test statistic obtained, x squared, is greater than the critical value from the chi-square table. For example, alpha equals to 0.05, in our example k equals to 3, degrees of freedom equals to k minus 1, which is 2. The critical value is 5.99, 5.99 given here, 5.99. Alpha equals to 0.05, degrees of freedom equals to 2, 5.99. And any values test statistic greater than 5.99 would be considered as extreme. But the test statistic we obtained from that example is only 2/3, which is quite small. So therefore, the null hypothesis is not rejected at the 0.05 level of significance. And we may conclude that the geneticist theory is about correct. And this is the one-way classification problem. So let's take a look at another example, example 23. Many horse racing enthusiasts are of the opinion that the pose position of a horse has an effect on whether the horse wins a race. In order to investigate this question, information was gathered on 160 races, in each of which there were 8 starting horses. So in this case, k equals to 8. K equals to 8. The number of winners from each of the pose positions is shown below, given here. Okay, the 8 pose positions out of the 160 races, 25 number of winners from post position 1 is 25, post position 2 is 27, post position 3 is 18, and altogether we have 160 races. Okay, the question is, do the data provide evidence to suggest that horses in certain post positions have a better chance to win a horse race? Use alpha equals to 0.05. Okay, so the first thing to do is to set up the null and alternative hypothesis. Now we have k equals to 8, so we need to specify the 8 probabilities, P1 up to P8. So what are the 8 probabilities? Okay, the question is, do the data provide evidence to suggest that horses in certain post positions have a better chance to win a horse race? Now, when we have no evidence, the null hypothesis would be that the winning probability is independent of the post position. It does not matter which post you are in. Okay, the probability of winning will have no difference. Okay, so therefore we let Pi be the probability of winning of the horse is in position I. Okay, the probability of winning if the horse is in position I, and therefore they are all equally likely without any evidence. Okay, so we have P1 up to P8, they all equals to 1/8. Okay, equally likely. Against the alternative hypothesis that the null hypothesis is not true, we have k equals to 8, and we have the expected frequency being 20 for each of the 8 cells. Okay, E1 up to E8 equals to n times Pi naught, which is equals to 1/8. So therefore the 8 EIs are all 20, and therefore by using the test statistic sum over x EI minus OI minus EI whole square divided by EI, we end up with a test statistic of 8.2. And I would like you to practice to do the calculation, which is 25 minus 20 taking the whole square divided by 20, which is the contribution to the chi-square statistic from the first cell. And for the second cell, we have 27 minus 20 taking the whole square. We have 7 square 49 divided by 20, which is the contribution from the second cell, and so on. And then by adding up the 8 contribution, you would have a test statistic of 8.2. Now at alpha equals to 0.05, at alpha equals to 0.05, what is the test statistic? What is the critical value? Now we consult the table. Degrees of freedom equals to k minus 1, which is 7. Degrees of freedom equals to 7. K minus 1 equals to 7 degrees of freedom. At alpha equals to 0.05, the critical value is 14.07. 14.07. So therefore the rejection region is x squared greater than 14.07 obtained from a chi-square distribution degrees of freedom equals to 7 and a level of significance equals to 0.05. So as the test statistic 8.2 is not greater than the critical value, so therefore the null hypothesis is not rejected at the 0.05 level of significance. Okay, so that's for the one-way classification problem. And the Pearson chi-square test can actually be applied to the two-way classification problem as well. So what is a two-way classification problem? Two-way classification problem. One-way classification problem, we concern with one classification variable. For example, whether you support, oppose, or have no idea, or don't know, neutral, towards CY being the chief executive. This is one classification, okay? One classification variable. And if we also classify the respondents by age, this is the second classification variable. Okay, so we have a two-way classification table. If we classified each respondents by age with 3 levels, and also by their opinions with 3 levels. Okay, so this is what we call the two-way classification problems. Okay, and this is what we call a 3-by-3 contingency table, where we have 3 rows. The first 3 corresponds to the number of rows. We have 3 rows, or the number of levels associated with this classification variable. The number of levels, we have 3 levels, and the number of levels, or the number of columns, is associated with the second 3-by-3 contingency tables. We have 3 rows and 3 columns. That means the second classification variable has 3 levels, namely the young age group, the middle age group, and the old age group. Okay, and we again will make use of this example. And more generally, we call this R by C contingency table. Associated with R is the number of rows, and C is associated with the number of columns. We call it R by C contingency table. Okay, now in our last example, we have the following. We have 3 levels of responses and 3 levels of age. And in each cell, we have 4 numbers. The first one is the observed frequencies, OIJ. Okay, observed frequency, like 17. Okay, because the levels had been swapped. The first level is don't know, and the second level is oppose, and the third level is support. Okay, for the neutral, the 3 numbers were 17, 70, and 84. If you take a look at here, so we have 17 from the young age group, 70 from the middle age group, and 84 from the old age group. So that is the first. That is the first entry in each cell, corresponds to the count. And secondly, opposed, we have 128, 196, and 178. For opposed, we have 128 young people, 196 middle-aged people. Opposed, we have 128, 196, and 178. And similarly, for support, we have 39, 113, and 165. 39, 113, and 165. Okay, 165. Okay, now these are the first entry. The second entry corresponds to the total percentage. Total percentage means, say, 1.72 is simply 17 out of 990. The total percentage, 17 out of 990, we have 1.72. The third entry is the column percentage. That means 17 out of 184. 17 out of the column total, 184, which ends up with 9.24%. 9.24%. Row percentage is 17 out of the total of 171. 17 divided by 171, so we almost have 10%. So these are the entries. So 4 entries. Okay, and notice that these are the column total, the row total. 17 plus 70 plus 84, we have 171, and this is what we call the row total. Okay, the total across the 3 columns, the total of row 1 and the total of row 2, the total of row 3. And similarly, we have the column total, 17 plus 128 plus 39, we have 184. This is the total of the first column. Total of the first column. And what is this row percentage? Row percentage, 9.94%. That means among those who gave a neutral response, 171, 17 of them belong to the young age group. Okay? Or what about the column percentage? The column percentage. Among those column percentage, for example, 50.02, among those people in the old age group, 52% support CY, 35% oppose CY. Column percentage. Column percentage is column among all those old people. 19% remains neutral, gave a neutral response. 41%. They said something wrong. Row percentage. Row percentage is 17 out of 171 and 70 out of 171, 84 out of 171. So the 3 must add up to 1. The 3 must add up to 1, the column percentage. Okay, so when we look at the column percentage, let's take a look at the row percentage. Okay, the row percentage for this one, 52.04. Okay, that means among all those who supported CY, 52% are from the old age group. Okay, 35% are from the middle age group, and 12% are from the young age group. Okay, and if we look at the column percentage, for example, we look at here the 3 column percentage. That means among all those young people, those who support CY, there are only 21%. 21% of the young people support CY, but 29% of the middle-aged people support CY. Okay, and 38% of the people support CY, and these are the column percentages, and the 3 do not add up to 1. The 3 do not add up to 1. Only the 3 row percentage add up to 1, or the 3 column percentage, this one and this one and this one add up to 1. Okay, so this is how we read from this contingency table. Also, we would like to say that this is a R equals to 3 rows, and C equals to 3 columns, and this is what we call the 3x3 contingency tables. And we denote the row total as Ri. Say R1 is the total of the first row, which is 171. R2 is the total of the second row, which is 502. And R3 is the total of the third row, which is 317. And similarly, we have the column total corresponds to C1, Cj. C1, the total of the first column is C1 equals to 184. The total of the second column is 379. The total of the third column is 427. And of course, the sum of the CJs must be the overall total, 990, which is equivalent to sum of the RIs. Okay, so we have the row total, we have the column total, and we have the frequencies. Okay, this is the setting of the problem. Now, the hypothesis for the two-way classification problem is standard. That means the null hypothesis is always specified as the row classification variable is independent of the column classification variable. In other words, in this particular question, the row classification variable is the responses towards CY, the supportiveness towards CY is independent of age. Okay, independent of age. That is the null hypothesis. What is the alternative hypothesis? The alternative hypothesis is simply the complement of the null hypothesis, that the row classification is not independent of the column classification variable, or simply the null hypothesis is not true. The null hypothesis is not true. Okay, and the test statistic, again, we make use of the Pearson chi-square statistic. same as before, we have the observed frequency minus the expected frequency, taking the whole square divided by the expected frequency, and sum over all the ij cells. Okay, sum over all cells. In a 3x3 contingency table, we have altogether 1, 2, 3, 4, 5, 6, 7, 8, 9, 3x3, that many cells. Okay, and we have the OIJs. This is O11, the observed frequency of the first row, first column, O11. O12, the observed frequency of the first row, second column, O12, O13, O21, O22, O23, O31, O32, O33, and so on. Okay, we have the same tail statistic, OIJ minus EIJ. Now here comes the problem. What are the expected cell frequencies, EIJ? Okay, OIJ is the observed frequency of the IJ cell, and EIJ is the expected frequency of the IJ cell under the null hypothesis is true, and is derived to be the expected frequency. EIJ is simply Ri times Cj divided by n, which is the row total, the corresponding row total multiplied by the corresponding column total divided by the overall total, So we have the Ri times Cj divided by n. Okay? So similar to the one-way classification problem, when n is large, the tail statistic will possess approximately a chi-square distribution. So we will come back to this part later. But let us try to figure out how to calculate the expected cell frequencies first. Okay? The expected cell frequencies. Here I input two more entries for your verification, okay, with the same example. Now remember, we have the frequencies. We have the Ri, R1, R2, R3, and we have the column total C1, C2, C3. Okay, now the expected cell frequency E11 is calculated to be 31.7818. But how? This is calculated by multiplying the row total. Okay, we have 011, the row total is 171. Its corresponding column total is 184. So we have 171 multiplied by 184 divided by n, the overall total, 990. We would end up with the expected cell frequency E11 being 31.7818. Okay? Similarly, E12, the expected cell frequency for the first row, second column. First row, we have row total 171. Second column, we have column total 379. So the expected cell frequency is 171 multiplied by the column total, 379 divided by overall total, 990. So we have the expected cell frequency of 65, and so on for the rest of the cells. Okay, you may want to check all the calculation using your calculator to calculate the expected frequency to make sure that you have no problem with this. Okay, and then the last entry is what we call the cell chi-square. The cell chi-square is simply for each cell, we have a contribution to the tail statistic, which is OIJ minus EIJ whole square divided by EIJ. And that is what we call the cell chi-square. So how do we calculate this part? The calculation of this part is simply OIJ 17 minus EIJ 31.78, taking the whole square, and then divided by EIJ, which is divided by 31.78. And we end up with the first term of the tail statistic being 6.87. And similarly, for the second cell, we have 70 minus 65.46 whole square. okay, which is 4 point something, and then divided by EIJ, 4 point something divided by 65.4, we have 0.3144, and so on. And we simply calculate the cell chi-square for each cell. And then the test statistic is just the sum of the 9 cell chi-square. And the test statistic by adding up these 9 numbers is 41.601. 41.601. Okay? And going back to the last page, similar to the one-way classification when n is large, the test statistic will possess approximately a chi-square distribution in repeated sampling under the null hypothesis. But now the degrees of freedom for the two-way classification test is simply r minus 1 times c minus 1, where r minus 1 is the number of rows minus 1, c minus 1 is number of columns minus 1. So here we have r equals to 3 and c equals to 3. So therefore we have degrees of freedom equals to 2 times 2 equals to 4. And by setting alpha equals to 0.05 with 4 degrees of freedom, alpha equals to 0.05, we have a critical value of 9.49. Okay, and the test statistic is 41.601, which is much greater than 9.49. So the null hypothesis is rejected at the 0.05 level of significance, and we may conclude that the two classification variables are not independent. But what is the meaning of not independent, and what is the meaning of independent? Okay, so for example, we simply take a look at the proportion of opposed across the three age group. So we should be looking at the column percentage, the third one. Okay, so that means for all young people, among all the young people, 69.57% of the young people oppose CY. But for the middle age group, only 51.7% of the middle age group people oppose CY. But for the old age group, only 41.69% of the old age people oppose CY. So you can obviously see a decreasing trend from the young age group to the middle age group and then further to the old age group. That is the association, means that older people tends to support CY more. Okay, if the null hypothesis is true that the two classification variables are independent, we expect these three proportions are more or less the same. Okay, these three proportions are more or less the same. Even for the option neutral, these three proportions should be more or less the same, and these three proportions should be more or less the same, because the age has no effect on the choice of the responses. That is the meaning of independent. But now in this case, the null hypothesis is rejected, and the interpretation is that we can see the age effect on the responses, that the young people oppose CY much more severe than the old people. Okay? Okay, so that's the two-way classification on the contingency table. So let's take a look at another example. The example sets the result of a survey conducted at Hong Kong U on whether there is a relationship between students' interest and performance in studying a foreign language. Okay, so we have a two-way classification problem. The interest of a student in a foreign language could be very enthusiastic, high, and average, that or I'm not quite interested, but I have to take a foreign language anyway. And the performance, okay, we try to associate the interest, the intensity of the interest with the performance, whether a high interest students will perform better, okay, according to this contingency table. And we have a survey of 220 students with the two-way classification table being tabled here. This is a 3x3 contingency table again, and the null hypothesis is there is no relationship between students' interest and their performance in the course, against the alternative that there is a relationship between students' interest and performance. Or you can simply write this as the column classification variable is independent of the row classification variable, against the alternative that the null hypothesis is not true. So again, we can tabulate this. These are the frequency 28, 17, 15, which is a reproduction of the 3x3 contingency table. Then you can calculate the expected cell frequency by multiplying the row total and the column total, and then divided by the overall total. The expected frequency of 16.3636 is a consequence of 60 times 60 divided by 220, and similarly for the rest, okay? And then we can calculate the cell chi-square statistic as usual. Okay, use alpha equals to 0.05, and from this table we end up with a chi-square statistic of 26.774. If you remember, similar to the last example, we have a degrees of freedom equals to 3 minus 1 times 3 minus 1, which is 4. And at alpha equals to 0.05, the quantile is given by 9.49, or the critical value is given by 9.49. And again, the test statistic 26.774 is much greater than the critical value of 9.49, and therefore the null hypothesis is rejected at the 0.05 level of significance. Okay, and what you can see here is that the row percentage, okay, the row percentage, we may compare the row percentage for each column. For example, for the column high, this is interest and this is performance. For row percentage, okay, so we have column percentage, row percentage, 1, 2, 3, 4, 1, 2, 3. Okay, when we look at the row percentage, okay, of the high performance group, or we should look at the performance of the low interest group. Okay, for the low interest group, okay, 46.67% of the low interest group have low performance, and 28.33% perform okay, and 25% of the low interest group perform good. Okay, but among the high interest group, it's quite seldom that they perform poor in the course, 15%, and among the high interest group, 50% of the high interest group will perform high, okay, which is natural, and 35% of the high interest group perform not so average, okay, which therefore is a clear indication that, you know, the interest and the performance are associated. Okay, and we are able to reject the null hypothesis. And I think the interpretation is an important issue if the null hypothesis is rejected. that somehow, for example, among all the people with high interest, among all the people with high interest, 15% of them have low performance, 35% have average performance, 50% of them has high performance. So among all those with high performance, most of them actually do come from the high interest group. Okay, high interest group. And that is the interpretation. And I think it would be easier to look at here. 69%, 57, 69.57 for the column percentage, 51.72 and 41.69. You can actually see a trend, a decreasing trend over the different age groups. Okay, so that's about the two-way classification problem, and that ends this course. But one last comment is that decision making, in making a decision, there are usually some other criteria or utilities that we have to consider. Okay, and these criteria are sometimes summarized in a loss function. And for example, this is what we call the Pascal Wager. Pascal is the famous mathematician Pascal, and he's trying to make some propaganda for the people to believe in God in the old days. Okay, so here is the problem. The fact is unknown to everyone. So the existence of God is unknown, whether this is true or not. Okay, but we have now an alternative hypothesis, or we have the decision. Okay, the decision is to accept the wager, okay, to believe in God. Okay, accept the wager to believe in God, or no, I will reject the wager and that I don't believe in God. Okay, you have two decisions to choose from. And the loss function is that if you choose to accept the wager, but actually God does not exist, okay, so what is the consequence? Believe in God and God do not exist, and this is a very limiting case, that hard penance for no reward. Okay, you pray very hard every Sunday morning, and you pray to God every Sunday morning, hoping that God will listen to you for 50 years, for example, but actually God do not exist, meaning that you have no reward. But your loss is quite minimal. Okay, not much to lose. Okay, but of course, if you believe in God, and the fact is that God do exist, okay, your belief will had been well spent, and you would end up with eternal salvation. Okay, but no wager, and if you reject the wager by not believing in God, and God do not exist, then that is the best scenario, that no penance, no hard penance, and just that. Okay, you haven't done anything extra, and you have no reward either. Okay, but if you do not believe in God, but God do exist, this is the limiting case. Okay, you make another error and you would be sent to hell with eternal damnation. So the loss is infinite. Okay, by rejecting the wager. So the decision will depend on the loss function. So the loss function will also determine the level of significance. Academically, in statistics, we simply ignore the utility function unless in some very subject-specific area. Otherwise, we just ignore the utility function by setting alpha equals to 0.05 in most cases. Okay, so there is and the consequence of committing a type 1 error, that is to reject a true null hypothesis, is not much, or at least nothing, or at least not much. And consequence of committing a type 2 error is accepting a wrong null hypothesis, okay, that you would end up with eternal damnation and you will be spend infinite time in hell. So if God do exist and you wager for God, the prize is an eternity of life, salvation. So that's the incentive that Pascal throw out to propagate the religion. And in Pascal Wager, committing a type 2 error leads to an infinite loss. On the other hand, your expected utility of believing God is infinite. As Pascal puts it, our proposition is of infinite force. Okay, so he throw it out as a bait to attract people to go to church. Now, here I have another example for you, which is an examination question in 2017 and 2018, and I would leave this question to you as an exercise. It says, in a study of coronary heart disease, subjects are cross-classified by the level of their cholesterol, okay? So we have two levels, either high or normal. Higher than or equal to 260 corresponds to the high cholesterol level group, while normal group is below 200 mg per dl. And we also have the age group. The age is classified into three age groups: old age group, middle age group, and young age group, with the specification here. And also we have a third classification variable, which is with or without a certain major symptom of heart disease, okay? With or without a major symptom of heart disease. So this table is quite complicated. This is not a two-way classification table, but in fact, this is a two-way classification table, okay? Classification of age, old age, classification of with or without a major symptom, as well as cholesterol level among the old age people. The two-way classification table for the middle age people, and the two-way classification table for the young age people, okay? And the questions for this question is, the World Health Organization reported that PC, the proportion of people who has high cholesterol level, equals to 0.5. And Williams suspects that PC in Hong Kong is higher because of the dynamic lifestyle here. The question is to carry out an appropriate test for Williams' suspicion at the 0.05 level of significance. State the null and alternative hypothesis, the test statistic, the rejection region, and your conclusion clearly. Now, how to tackle this problem? This problem is only interested in the proportion of people who has high cholesterol level, irrespective of their age and irrespective of whether they have a major symptom of heart disease. So all we have to do among the 1,700 respondents, how many people has cholesterol level? Okay, we have 50 plus 50 plus 180 plus 220 plus 160 plus 240. Only these people has high cholesterol level. And this question is actually testing for proportion equals to 0.5. Okay, proportion of people who has high cholesterol level, P equals to 0.5. Against the alternative hypothesis, P greater than 0.5, P greater than 0.5, according to Williams' suspicion. Okay, so this is the question. 100, 400, 500, 900, okay? 900 out of 1,700. So the sample proportion is slightly greater than 1/2. So the question is whether this is greater than, P is greater than 0.5, okay? And that is the question for Part D. And the question for Part E is from the Census and Statistics Department. The proportion of people in the young, middle, and old age group are in the ratio of 5 to 8 to 6. Now, AD suspects that the sampling procedure is biased, that the 3 observed proportions in the sample are different from those reported by the Census and Statistics Department. And the question is to carry out an appropriate test for AD's claim at the 0.01 level of significance. State the null and alternative hypothesis, the test statistic, the rejection region, and your conclusion clearly. In this case, what we are interested in is the 3 levels of age only. That whether the 3 age groups are in proportion of in the ratio of 5 to 8 to 6 in the sample. So we are interested in whether this group, how many old age people do we have? We have 500. And how many middle age group people do we have? We have 700. And how many young age people do we have? We have 500. Okay, whether that's in the ratio of 5 to 8 to 6. Notice that this is young 5, middle 8, and old 6. 5 to 8 to 6. That means 5 to 8 to 6, the other way around. Okay, so this is a one-way classification problem, and all you have to do is to add up the number. 501 equals to 500, 02 equals to 700, and 03 equals to 500. Okay, and then you carry out the one-way classification problem according to this proportion. And the third question is to carry out an appropriate test to determine whether the presence or absence of the major symptom of heart disease is associated with the cholesterol level of the patients at the 0.05 level of significance. Okay, now this is a two-way classification problem, but we have 3 classification variables. So you have to determine from the question which 2 classification variables are we looking for. Okay, we are looking for the presence or absence of the major symptom of heart disease and the cholesterol level. So all we have to do is to ignore the age, okay, by adding up how many of them are of high cholesterol level and with the presence of the major symptom of heart disease. So we have 50 plus 180 plus 160 as the first one, the sum of the frequencies of all age groups. Okay, 80 plus 45 plus 10, 50 plus 220 plus 240, 320 plus 255 plus 90, and we end up with a 2x2 contingency table only by ignoring the age. Okay, ignoring the age. And then the last question is to carry out an appropriate test to determine whether the presence or absence of the major symptom of heart disease is associated with the age of the patient. State the null hypothesis, alternative hypothesis. This is also a two-way classification problem where the 2 classification variables of interest is the presence or absence of major symptom of heart disease and age. So we would have a 2x3 contingency table at the end, 2x3 with or without and age groups. Okay, 2x3 contingency table. You have to play around with the frequencies. Okay, and thank you very much, and that's all about this course, and this is the end of all the lecture material. And just in case you have any problem, please don't feel free to send me an email to ask the question, or you can also send an email to the course email, or you can post the problem on the Moodle forum. You can play around with you can download the past examination questions and play around with the contingency table, which is particularly a very simple approach, nothing very special, but a little bit computational tedious, particularly when there are a lot of rows and columns. Okay, thank you very much. Good luck in your examination and stay safe. Okay, bye-bye.